Okay.
Perfect. Thank you, Bob. Thanks, Trip. Hello, everyone. Please, Bob, tell me if you will see my screen changing. So I wanted guys to go through the some evolution of the format we are facing today and we faced in the past, and what was the impact on medium. So basically on coax fiber and so on. So I think you will find this really interesting, and I want to do that like a future-looking kind of presentation, and hopefully you will not get bored by my style of presenting, and you will enjoy until the last minute. So let's jump in. So who am I? The question you may ask yourself is, who is this guy coming from? Like what his background is. So I started my career at Miranda. So basically I did 7 years there. For those who are familiar, I invented the Kaleido-X in collaboration with a group of engineers. After 7 years, I decided to continue my journey to a different path. So I founded my first company, which was a design house. And then I saw some small connectors and I thought to myself, oh, we can use that as pluggable. And the goal was, that was the goal of Embryonics, enable you guys in media, AV, and broadcast space to really change easily the IO types. So HDMI, coax was really the thought at the beginning. So Embryonics was acquired in 2019, just before the COVID. And like I said, I'm really passionate about technology. So hopefully I don't go too much in detail, and you, like I said, you're still interested by the presentation. So let's go and talk about these format and what they affect on the medium we're using. So let's go back in time if you don't mind. So the first, let's see at the SDI evolution. So the gray bars are really the evolution we remember from SD, SDI back to UHD 12 gig. And I don't know if you knew, but there's a new standard. They're trying to push 24 gig. I have no clue if it will be on coax or directly fiber. And as you can see, the gray, the cable evolve in time. But one thing that all these format have as in common was really a single connection or a single let's say signal there, and a single SDI. And then the fiber, the SMPTE 297 was released in 2006, enabling us to do single mode, multi-mode, which was not that popular in broadcast, a little bit more in media space. So this also enabled us to do CWDM, and I will really come back on this CWDM in the next slides. But there's another change that happened, and Embryonics was one of the first jumping on in the boat on that, was the Ethernet IP connectivity, like 2022-6/2110. So the goal here, it's not really to jump in these standards. I will be pleased to come back if you want Riedel to talk a little bit more about these in today's world. The goal is to show you that with sample IP connection, we TDM the data so we can pass more signal. And I will explain later what I mean by that. So one coax mean one signal, fiber open some doors, and IP open more doors that we will check. So let's talk about fiber for a second. Without going too much in detail, the single mode fiber mean you have one mode of propagation, and the multi-mode is multiple modes of propagation. Thing with the multi-mode is, because you have those multi-path, you will kind of reduce the distance you can achieve. A laser will be cheaper, and I put there, for your information, guy, I put there the type of lasers. It's really for people that are curious or geek like me. So there's two types in single mode, which is the DFB and the FP. And there's not now the new VCSEL, which is not new anymore, but it was vertical cavity surface emitting laser. So this is more for multi-mode. And again, it's just curiosity, guys. So what thing to remember there, it's single mode, one mode of propagation. So this is also a graph that is a little bit detailed, but let me explain it to you. It's evolution in speed of optics. They realize that there's a limit in technology they will face, and then they have to say how much we can push the envelope, or let's say multiplex that. And one thing they did is wavelength division multiplexing. So see the fiber as an highway. You have multiple lanes, you have small car, and you can place multiples in it. So what this mean for us, it's mean that you have 18 bands. You can see the drawing in my screen. So you have 18 bands, and in each one of their bands, you can send one laser. So in like practical number, I can send 18 12 gig on single fiber. So which is pretty good. You have to be aware of one thing, and you see it in the graph. It's called the water peak. So basically, the lights will reflect with the O2 in the water molecule inside, and will kind of block the light, so attenuate more the light. Again, this is really deep, so I leave you with this drawing. So now, when I did this presentation, it's really interesting. I love to do that, guys. I learned some new stuff. So this is for the geek or curious only. So if you can turn off your camera for a few seconds if you don't want to see that. It's really, really quick. So I found on the holocore photonics. And there's one interesting point there. You know, we always say fiber, the speed of light. Basically, because we send it over glass, it's 30% less fast than in the air. So DARPA, to be able to do like quick communication, they decided to do this photonic crystals, and they were able to reach 99.7% the speed of light. So you're really at the speed of light. So just be aware of that. I think it's a good, I found it really good information to know. The fiber, as we know, is 30% slower than the light in the air. What's this look like? It's really funny. It's tube. It's not, they didn't base it on the density of the fiber, but more the loss. And if you can see my cursor here, the last one they did was what they call it the nested nodeless. And here what it looked like. So this is really small tube. And this crystal will enable us to really send data or send signal over. And thing is, you have to remember this is really for higher speed, not really for really travel time. So this is why DARPA is using it. And I found it really interesting to show to you my discovery. Of course, I did not discover that, but I discovered this exists, and it's really interesting. So now, first learning. With the speed evolution, so moving to 12 gig mean that we had impact on the medium. We go from a coax that was okay, a lot of lost in high speed. Like, and again, if you want to go into geek things, you can look at tangent lost. So really big when you go up in speed, and then we move to more advanced coaxial cable to really minimize the speed when your signal going faster. We did not find there's a way to put multiple coax in one big bundle and send like data over, but the fiber enable us after to say, okay, I can send more data, send more signals, send more SDI per fiber, which really minimize the cabling. As you know, fiber is really lightweight, so it's really more minimize also the weight. One thing you have to be aware, it's fiber, it can be tricky if it's not treated properly on the end. You can scratch it, and then you have a big delay, a big insertion loss or reflection loss. So then your bandwidth, not bandwidth, but your margin are affected in optical. So let's see now what we do in the really the IP world. So I will say what's the next step in media, AV, and broadcast was really this IP. So IP is everywhere. Now it's really real. We see deployment in the market. So what's really this give us as an industry? So let's take a look. So I put here the biggest addict of speed is the broadcast. So all our signal are big, meaning video uncompressed is quite of big. You can see there, it's really interesting. This came from Internet Alliance. You can find this drawing on the web for your own presentation, or if you want to read more about it. But let's go really quickly. So if you look, automation is where the speed was really slow. It's going to the range of 10 to 1 gig. So this is kind of, I joke all the time. I say this is DC. It's not high speed anymore. And then you go to the automotive. And remember, 5G and automotive are really connect to each other. Why is that? It's because the sensor we'll put on those cars will be in the sweet spot around 5 gig. They can ask for more bandwidth, but not like 100 gig of data. So about 5, 10 gig, this is what we expect to have. So probably after 5G, it will be something even faster, probably 6G, right? So in the enterprise world, we go from one gig to 10 gig, 100 meg to 10 gig, and you can see we go to 10 for 50 gig. More and more enterprise need those bandwidth really to for all the daily jobs. So then you move to the cloud providers, and cloud providers were 25, 50 gig before. Now they move to this 100 gig era and also 400 gig. And then what I put you see the red bar here, we're almost full throttle there. You have the really people needed like big service provider like AWS, Google Cloud, these guys. And you look here, it's pretty amazing. Oh, sorry. So it's pretty amazing. They go to 1.6 terabit. And then probably some of you are really technical. You will ask yourself, how can we do that? How can we go to 1.6 terabit? And let me explain how they did it. Really interesting stuff. So here's the path. And basically, the cool thing for you to see is we are at about 400 gigs. So if you try to find pluggable at 800 gig, it's the early days. So 800 gig, it's the next stepping stone or next step. Then we move to 1 terabit. Then we move to 1.6. And if you look here, they didn't place any time on the 10 gig, but they 10 terabit, which is far from 10 gig. But the 10 terabit, they did not put a timeline on it. So basically, that's really the speed we can envision moving in the following years. One thing cool you have to see, I know my slide has a lot of text, so this is, you can look at it maybe after, but it was kind of 2002 to 2016 was not a big step. We increased by 2.5 times, but then we reached the peak with 25 gig and then 400 and so on and so on. How they do that? You guys that do that remember analog times will really like that, and RF as well. So they use modulation now. So they will use what we call a pulse amplitude modulation, and I describe it in a slide after to really so those are less technical will understand really well. The PAM8 as well, and then they want to move to QAM, so quadrature amplitude modulation. So let's continue on that. So here's the speed, like if I define it like in terms of really years. And as you can see in the graph, and again, this is from Ethernet Alliance. I didn't create anything here, guys. So we are at 400 gig. We are 200 gig, 50 gig, and here it's what people start to work on. So 800 gig pipe, or let's say connection. Let me refer that as a connection or a link between a switch and an equipment, a switch and another switch. And I will go back in details of what's this mean for us? What's in it for us in all this? Because right now I know it's just going in speed, but we will talk more about HD 3G signals soon. So here how to do it. It's really interesting. So one is multiple lanes, like multiple coax, you will tell me, or like multiple fibers, and you're totally right. So multiple lanes, and the other one that is really cool, it's the multiple steps. Think about your ladder as a bit interval or a symbol or just a unit of time. And then you put multiple steps. And the multiple steps, instead of being 0 and 1, it's now 0, 0, 0, 1, 1, 0, 1, 1. And you have 2 bit per one ladder. So you have 2 bits, so you can carry double your speed without like going like a smaller, think about a smaller ladder that you cannot climb on it. So, but they keep the ladder the same way and they just add steps. So which make them like go really fast, or let's say faster. So here's what it's look like. And I know this drawing can be confusing, so I will take 2 examples. So the first example, and I'm running at 25 gigabaud. So my ladder, it's 25 gig. Then I will use like the coherent, which is, I will not go in details, but the coherent is a PAM, but also quadrature modulation, also polarization modulation. So I can do 4-bit per 25. So here you look, okay, 100 gig lane. So this is 100 gig with only 1 fiber, which is pretty impressive. The other way of doing that also, it's to say, okay, let's go with twice the speed of my 25, so 50 gigabaud speed, but let's do more lane. So first I do PAM4. So each one of them are 100 gig, and I can add 8 of them. So now I have this 800 gig, like 50 gigabaud, and multiple step. So you have the 800 gig, and this is what's coming in the coming years. So maybe 1, maybe 2. I know people are working on it. There's demonstration, but not a public like. I think they start releasing the QSFP 800, and I will come back to that. So this is just a slide to show you that in 2018, they were able to send 112 gig. So why 1112? It's really the, when we send the payload 100 gig, we always add scrambling. So this one is probably 66, 64. So it's an encoding to make sure you have enough transition. So let's think about 100 gig Ethernet. So April 2018, they did this. It's 3 years old already, and we start seeing it. So quick evolution of form factor. Now it's good. I talked to you about the speed. I talked to you about, yeah, what it's mean in terms of like one lane, multiple lanes. But for IT and IP world, they define what they call the pluggables. So what's a pluggable? It's basically, except this guy, which was not a pluggable, but it's part that you can answer in a switch and basically have an SFP, QSFP, and then you can connect equipment. So the before going, I don't want to go in all the steps, but the interesting part you have to check is everything that is kind of single lane go back to the SFP. So the SFP, it's a small part. I will show you dimensions in a few slides, but it's really I call it like unique or one in, one out. And for other parts that they need 8 lanes, they will go with QSFP. So now they're reaching what they call the QSFP DD for 400 gigs. So this guy will have 8 lanes in each direction to do your 400 and to do your 800. So it's 4 laser in, or sorry, 8 laser in, 8 laser out, photodiode out, sorry. So laser and photodiode to do your complete path. So that's the evolution. And the cool thing is there's also an SFPDD that will do 100 gig for you. So a single part will have enough power to do that. And this is available from all the IP vendors. You can find them on Google, Arista, Cisco, all the switch vendor have their own. So this is really a nice technology that a lot of vendors or switch vendors like accept and approve. There's also the OSFP that you have to see here. The OSFP was mainly pushed by Arista to really create, but there's a group now that taking care of that. And they say when the density will become like really hard to do in QSFP, they said OSFP might make more sense. It's a little bit more width. The width is a little bit more large. So again, I don't want to go too deep in details. I hope it's still okay for you guys at this point, but let's jump in what we will see. But before that, a QSFP DD today can carry up to 183 gig in there. So, but you will tell me, yeah, but I can do that with like CWDM and multiple fibers. And you're right. The thing is, you don't need like mux and demux to do that. It's really, really TDM. It's really 8 laser, 8 photodiodes to send your data over. But it's not too far from CWDM if you can afford all the mux and demux and things like that. But this is more dense solution, and in the IP world as well. And the other one is we can transmit 45 3 gig in a single SFP. So this start to be really impressive as a number, but this is where we heading in IP world. So the two most popular parts you will see or you will face or play with, and I could have spent an hour talking about them, honestly. And I don't want to go again too much in detail, but there's multiple types of connector. You have the LC, you have is my drawing show it. You have the NTP, you have the MPO. But basically, the module it's about set 7 centimeters by 2 centimeters. I'm so sorry I don't have them in inches. So you can do the math. I'm really sorry about that. So, but basically they're pluggables, and this is QSFP 28 for 28 gigs per lane and DD. So on the most popular one, the SFP28, basically you have multiple types. So if you look at broadcast, you will find those with coax like HDBNC. But if you stick with the IP ones, they will have fiber optics, so LC connectors most of the time. Some, again, broadcast SFPs sometimes as ST connectors to be more ruggedized. But the SFP standard one have LC connectors. And you can see the size of it. It's about, like I said, 5 centimeters long by 1.3 centimeters width. So really small guy. And when I started my career, I said to people, one day we'll see the 1112 gig in an SFP. They kind of said, no, it's impossible. And we will just about to see them soon. So I'm really glad that this move on, but it's moved faster than I even thought. So but okay, again, it's really cool. It's higher speed. But what's in it for me? I will not talk about the really advantage of the 2110 or 2022. Again, I could have spent another hour and more on this subject. I want really to focus on the number of let's say video we can carry on. So let's start with numbers, and I think you will see me. I found it a lot mind blowing. So I start with 4K. So in a 800 gig, again, in a small cable, sorry, 2 QSFP can carry 76, sorry, UHD. And cool thing for you to see down, I put in 2110 because I don't send the blanking, so I'm at 10.5 gig. This is 5994 that we're used to. So this is about the bandwidth I need. But you will say, hey, no, you can push a little bit more than that. You have to keep some room there, and there's papers on that. You don't want to crank 800 gig. You can do it, but I put a mark there. I say 76 is something where you can be comfortable. Yeah, it's about like 20 gig of extra just for PTP communication and so on, and any reordering you have to do, or any not conflict, but bandwidth usage. So I also put this slide for you. So 800 gig will enable you to carry 300 plus 3 gig signal. So you can double that 600 if you look in HD, pure HD, no 3G. So you see the number are really scaling like crazy. But the next one, in a 24 port, like 400 gig switch, you will be able to pass 910 UHD signal. So just put that in 3 gig. You can kind of multiply by almost 5. So you look at this and you have a huge router there. So it's nothing comparable with the with SDI in the past. And this is just a 1 rack unit. There's bigger switch with more 400 gig port in there. And this is 400. Why I put this instead of 800? It's because this was up to date. So up to date, since when I did this presentation, I just saw 400 gig 1 rack unit. And again, if we compress in an 800 gig, we'll pass 740 plus UHD. So you will say, okay, you have to stop at some place, but this is just to show you how many signal we can go inside. And again, if you said CWDM can do that, you're not wrong. You will just take more space to put fire like mux and demux and things like that. So this can be done with a single connection, no mux and demux. So what is the other impact? And you see me coming. Now we talked about the speed. Now I'm talking about the Moore's law and what's this will affect the pluggables in the future and also affects everything in our life, right? The miniaturization of computer, your cell phone you have in your pocket, all this. So let's talk about Moore's law a little bit. So this is something I found in Wikipedia, but people may say to you it's double every 18 months. Others will say 2 years. Others say speed and capacity will increase every couple of years. So I just put it there. Let's keep in mind, or let's just assume something. Let's assume that the Moore's law will define that we will double every 2 years. So I found this slide interesting, and again, it's just to show how it's kind of speed up. So you see, the transistor was there about 60 to 70 plus, and then we moved to like all integrated circuit, and you can see it's really hard to see, but here you have an expansion. It's really scaling really fast. And I have the next slide that will show you that. And if you're curious, honestly, you can like connect me on LinkedIn. We can go and I can talk with you about the quantum computer and things like that, what we can do today. Really interesting stuff. But this really scale and it's faster and faster and smaller. But what smaller means, and I say that as my road to tiny transistor. I put invisible first, but I say tiny, it's better. So let me go in some notes there. So first of all, the white blood cell that we have, it's 25,000 nanometers. So 25 micron. You say, okay, it's cool. Transistor, it's 7 nanometers now. So it's 3,500 more dense that or white blood cell, and I'm like, oh my god, I can put a lot in. It's like I put 3,500 in a row, so which is kind of mind blowing. And there more stuff to come. There's 5 nanometers they're working on, and other stuff like carbon fiber and things like that. So carbon tube. So it's kind of never ending story. So now, if you want to talk about something that you have close to you, if you have like me a Core i5 from Intel, like old generation, your computer has just the CPU has 1.4 billion of transistor there. And we're looking at this and say, yeah, but again, what's in it for me? What's in it for us is we can miniaturize a lot of thing in life, and pluggables are not the exception. We can miniaturize stuff to fit in pluggables. So I found it really interesting. I started with the human hair, by the way. I have to really talk about that, but the it was too big. I say it's too big, so I need something smaller. So I guess I could have used the red blood cell as well. So let's look at the early days of pluggable. Now you see me coming. Now let's go in what's in it really for us as a market. So at the early stage, people were doing like basic functions. So on the left side, it's really for telecommunication usage. So you have you can look for smart SFP. You will find the companies there. So it was for network migration to the gateways there as well, but also timing and also monitoring. They were really looking at monitor errors and also do reflection to check the payloads coming in and out from a switch. And this was super popular at maybe 5, 6, 7 years ago. On the broadcast side or AV and Pro AV, we did one that is SDI to HDMI. It was really be just converters. Instead of having a box that you put inside of your equipment, people designed it with cages. You plug the SFP in, and boom, you're good to go. You have your converter built in. So you save space, you save amount of power, you save cabling, you save power supply, or let's say wall mount power supply. So that was the old days, or not old, I should not say that, but this was the early days of pluggable. So now, interesting. So we see two things before I jump in the last section of the presentation. What we saw was the more law mean more processing for everything. So we should not take granted that cards has to be cards and big system and big iron. It's has to follow the same rules of miniaturization. And the other thing, adding signal means that we needed to find different ways to really same things like miniaturize, but also minimize the rack space. So CWDM was great, but IP, it's another way to do that. So IP help us to do that. So let's see the advanced pluggables. So first of all, the evolution. There's a couple of vendors that are active in this field. So the first one I want to show you, it's a really interesting one. It's opto oscillo quartz, as you can see in my reference in my slide. Let's say you are in a remote production environment or a small studio or even a lab, and you said, I need a PTP to black burst. And of course, in a real studio, real environment, you want to get a good SPG or two big Grandmaster, but sometimes these guys will do good for a redundant Grandmaster. They're really, really acting like a grandmaster. They're fully compliant with everything, and they do a decent job. Thing is, they cannot connect to too many loads. They cannot have many slaves. So if you have more than 64 slaves, you're starting to have trouble. So then you have to use switches that are boundary clock, and then you can address more. But just keep that in your pocket. If you go with 2110 deployment and you say, oh my God, I need a redundant PTP. So you can contact these guys, Oscillo Quartz, and you can have a GPS and another Grandmaster in your system. So the other extreme ones are able to do multiple functions. So we kind of pushed the envelope a little bit. So we did first NCAP and DCAP, it's software defined, and then we pushed JPEG XS, J2K compression. And as you can read there, we can do multiple of them. But what's the miniaturization allow company like Oscillo Quartz and Riedel today? It's really to have this software defined because there's enough space to keep multiple version or upgrade and stuff like that. So they're now based on pure processing. So here you have an example. Also the SFPs, the let's say broadcast and media SFPs really improve and give more functionalities to a bunch of appliances you have out there and parts you already use. So they can be, and still they can be full SDI or they can be IP. But basically, if you have, let's say, we did a press release with Fabrics and they put in like a 2110 gateways in. So you have all these kind of products. So these products can really benefit from the pluggable aspect we have. So, and I mean have in terms of the broadcast, media and AV industries. So it's more, it's a software defined, and so it's not just a gateway anymore, those parts, like most of the products, right? They're not just an audio router anymore. They're not just a converter, because we are able, with miniaturization and the speed, we're able to do up-down cross, we're able to do compression. So not only us, everyone with this miniaturization pipe and the high speed of the Ethernet can do such things. They can miniaturize, they can really do more processing with less space. So they are not just a multi-viewer anymore. And the last thing we pushed the envelope was really to fit a 16 image multi-viewer inside. So like a complete multi-viewer, not with all the bells and whistle, but really, really advanced, so production can be done with this multi-viewer. And again, if you're stuck in a production, you need something quick, you plug it in and you're good to go. And it's not just an SFP anymore. So there's two types now of pluggables you have to know of. One is the standard one, which is the IP commodity and also the connection pipe. And the other one, it's the advanced one. It's an IP processing, it's an IP connectivity part. So the thing is, it's really advanced, so you need to fully benefit from it. Sometimes you need like homegrown switches or appliance to do that. But basically, these are now the advanced one, the extreme one, and I'm sure like my other market will jump on this miniaturization pipe for the pluggables, but also in broadcast there will be more people jumping in, and like I said, these will improve your current products if you have a need on that. So that being said, I think they always told me I speak too fast. So that's will all be also be the case today, guys. So Bob, it's back to you.
Wow. Can you hear me?
Yes,
That was incredible. Oh my gosh, I want to watch the whole thing again.
I'm
Um,
sorry. I'm
that
sorry, guys. Everyone, I'm sorry. I speak
that
always
was
too
so good.
fast.
That is, man, I'll tell you what, the bandwidth that we're pushing on the fiber today and what you showed is just absolutely incredible. When, like you said, I know some of the long haul carriers that are was doing 100 and then 200 and then 400 gigs, and with multiple DWDMs and everything else is absolutely incredible when you're talking up into the terabits of data on something smaller than a piece of hair on our head. um, anyways, let's see if we have any questions. Hold on a second here. I've been watching. Okay, so we got a question. So if I buy a 400 or 800 gig switch from someone like Arista, let's say 4 or 8 by 100 gig ports, how do I know which SFP type to choose? For example, I want multiple JPEG XS streams versus SMPTE 2110 or a multi-viewer solution. And how about monitoring? Great presentation.
Okay, thanks. So I will say the switch you will buy will okay, if you go to, let's say, the top of the line today, 800 gig. So first you have to know that they will be compatible with 400 gigs. Usually not going too much in detail, but also these will be what we call really the spine. So the spine is your core, is where and the spine leaf are really not limited in terms of, they are always limited, but they have so much bandwidth internally for the networking chip that you will be limited by the IO. So my advice will be, if, because price is not that great of a difference, if you're okay, you go with 800 gig, then you check with Arista for their, let's say 800, and then you can go to Leaf to really scale that. Because the reality is this 800 gig, like JPEG XS, you will probably need multiple switch to be able to process that, because I'm just talking about the transport. Then you need all, let's say, intelligent SFP to compress that. So we can do 2 channel of JPEG XS in UHD. So then you will need 400 of these small guy or other appliance. Some will be probably do more JPEG XS per rack unit. So there's all this question. So I don't know the person that wrote that to you, Bob, but they can connect with me on LinkedIn and we can certainly continue the discussion. So now for multiple 2110, again, it's just a question of what you want to scale. And go back in my presentation in the numbers, you will see I really like these. Because people think 12 gig is 12 gig over IP. And a cool story there, I was with one of my engineer and he came to me and said, look, I don't see 12 gig in my 100 gig. There's something wrong, something broken. I say, are you in 2022-6? Which is not, I knew it was not doing UHD. So are you in 2110? They said, we're in 2110. So I said, 2110, you remove the entire blanking. So you're not at 12, you're 10.6. So then you have to think about how many I want to scale. If your equipment can do UHD, how many you want to pass in, how many you have in your studio. So the switch for me will be the end thing you will do. You will count number of like JPEG XS or number of 2110 you need, and then you move to the design. And I don't want to plug that, guys, but I did some videos. You can look at Renault Talks IP. There's nothing on products there, but you can find this 2110 versus 2022. And also we will push a monolithic switch versus the spine leaf. So I
Great.
hope I answer your question.
Yeah, that was from Luann Linneber. Awesome. And by the way, like just real quick, you mentioned on the JPEG XS, you know, I remember at IBC a year, 2 years ago now, you know, where we started out with TICO, you know, at 4:1, and then we
Yep.
started doing JPEG XS. And the whole thing there was right at 10:1, everyone wanted to get down below a gig, right? So I think you guys were showing, Intupix, right, was showing the
Correct.
you know, UHD at about 875 or something like that, right? About 900 megs or something.
Yeah, that's correct. If you want to keep a good quality, let's say, it will
Yes.
be visually lossless. You can go close to 10:1. If you're more on a monitoring or return feed, you can go to 20:1, from my understanding. This goes beyond the JPEG XS. This is what they will call TICO XS, which is not an add-on, but more compression you can achieve. But this will be really visually, you will see some degradation
Yeah.
of the picture.
Yeah. And the other thing that's incredible is the low latency, right? Because it's line based, not frame
Yep.
based.
So yeah, it's
Good.
about 21 lines back to back. So
Okay.
yeah, that's pretty good.
That's a good number to remember. Okay. Next question from Philip Grossman. So early SFP with ST2110/SDI gateway ability ran really hot. Has this been solved?
You know, that's interesting. It's a good question. Of course. Okay. So just a side note on that. You know my background, Bob, right? I was at Miranda. So when we were designing back then, and you can look, it's all public. Companies were doing 1 rack unit of multi-viewer, 16 image, and the one we did was 45 watts. So I'm not a magician, I have to say. I don't have a magic. So one and remove that. We went from like 45 watt to about 6 watts. So now you will tell me 6 watt in such small guy could be critical. So in an appliance we were okay to really reduce that drastically, that you will not burn yourself. Thing is, I compare that between a motorcycle and a car. You can touch the engine of your motorcycle because it's so close, right? On the car, you have the hood, so you cannot do that. But I can assure you that inside the SFP, temperature could be way lower to other competitive solution, but you're not able to touch it. And keep in mind that the engine, it's almost the housing you're touching. And I did also a video on that, Bob. So if you're the person that asked the question, you can go there. I go in physics and details, and I'm not scared at all. The SFP, of course, because their engine, you're touching the engine, they will be a little bit more warm than a car that you touch the air. But it's interesting. Again, it's perception of things that I have to say.
Cool. The next one's from Robert Castro. How much of this technology is radiation dash hardened so that it could be used in space-based applications?
That's interesting, Robert. I guess we should talk after the call. We did not design it to go in space. That being said, I know some people tried with the HDMI we did. I have to say it's a complete block. So EMI wise, it's really good, but I have to say I will, Robert, I will be honest, I cannot really answer your question. It's kind of, I will say it this way, it's over my pay grade. We never tried, so I think we should try at some point, and I'm interested in continuing the discussion on this one.
Okay, I can send you Robert's contact information.
Perfect.
Okay, next question. From Philip again. Are the JPEG XS, ST2110, etc., clean and quiet switching?
Okay, so when we started, it was not. We had this feature. Soon we realized And yes, it's clean and quiet switch. The end cap, we had the frame sync built in as well. So, and again, we learned that from different deployment we did. At the beginning, we thought that it's kind of a perfect world when PTP and Blackburst are aligned. We soon realized it was not the case, so we add this frame sync inside. We also add all the 2022-7, so redundant path A, B, and D, A and D, really to and JPEG XS, J2K, we're adding more buffer now to really cope for the one jitter and features like that.
Yeah, I know one of the manufacturers, they call it, you know, break before make or make before break, right? Is what
Correct.
some of them call it.
Correct. So we can do both. But again, it's depending of how 25 gig you use it. If you use 2 UHD, we have to break before make, right? We don't have enough bandwidth in the 25 gig to have 3 UHD at the same time. So we'll break, but if you have, let's say, HD in there, we can do the make before break.
Yeah, and by the way, in my experience, I was playing with the 2110 router during COVID for a long time, and honestly, even the break before make, I mean, to me it seemed to hold up better than a standard SDI router, right? I mean, like you hardly ever see a hit or anything. It was incredibly clean.
Yeah.
So very impressed.
Yeah, I think and on this topic of the IP, all this the market, I have to say all the vendors were super collaborative in working in these interrupts, like NMOS, 2110, 2022. You know, when we started, we were only like 5, 6, and it was really hard to have something like working. And at the end, the guy told me there were about 60 companies jumping in, which is really good sign. So, and personally, I think now the transport level 2110, it's all there will be upgrade, recommended practice, and things like that. But we are at the level now to work on, NMOS and discovery registration. That's really where the industry has to focus. I mean, the manufacturer has to. We have a responsibility to really invest in there and really make this move even faster. And then we'll have the securities coming and things like that, which will be something we need to do as well.
Great. Well, I think that's the last question. There's some good questions there. Yep, I think that's the last one. So, well, thank you so much. That was awesome presentation.
You're
a lot
very
really
welcome.
good information.
Sorry, guys, to make it short. And again, thanks, Bob, for having me. Thanks, Trip, for organizing it too. So if you have more questions, following up questions, Bob, please feel free to share it with me and Trip, and we'll make sure we answer to your fellow in Atlanta.
Absolutely. And I hope to see you in October out in Las Vegas at NAB.
Yes, I'm missing it. So yeah, I will be there for sure.
Back on the floor again.
Yes.
Thank you,
Will
Trip.
be good.
I see you're back. Well, thank you guys again, and thank you everybody for joining us. And we're already working on the next meeting, so we'll send that out as soon as possible. And thanks again for everything, Renaud. That was an awesome presentation.
Thank you.
Thanks a bunch for having us, Bob. Appreciate the opportunity.
Thanks, Bob.
All right, take care, guys. Thank you.
Thanks. Bye.